Okay. Okay. So good afternoon, good morning to first joint Shinigami Raito community call, and maybe I will start with explanation of this confusing thing with names that we done last week. Because in the expression team, we have two Cairo-based Bitcoin-related projects, and they were named Raito and Shinigami. But we realized that that creates a fragmentation of communication, and that we need to communicate twice about more or less the same thing. So we decided to join both the projects and Telegram groups, where joining projects is maybe not that clear right now, but definitely we will need Shinigami script interpreter in Raito consensus client. So that's the connection we want to be explicit from now. And I think that generally combining two communities that are not that different, by the way, will make work easier. So we already joined the Telegram groups. Probably we will also rename GitHub projects. Shinigami will become Shinigami script, and Raito will become Shinigami consensus, and Raito name will hopefully disappear and will not create confusion anymore. Is that clear, more or less? Okay, so maybe I will start with a brief description of what we want to do. Let me share my screen. Hey. Okay, so maybe we should start with where we want to be at the end of that project, or maybe even at the end of the project that will maybe be a continuation of current effort, because I'm not sure if we will manage to get to the end goal in a single exploration project. But what we would like finally achieve is to have a start proof of state of the Bitcoin chain at some block, possibly at the last block that Bitcoin produced, and that chain should include an UTXO accumulator, which means that such a proof can be used to do many things, like initialize a new Bitcoin node without having to download. Sorry? There is some noise.
Francis, you are not on mute.
Okay, thank you. So initializing a node without having to download and process all historical block is one obvious application. Having a light client that downloads proofs instead of blocks and having and processing those blocks is another one, and maybe there are others that we do not fully realize right now. And in order to create a proof, we need to do some Cairo processing, and this Cairo processing result in a proof auth of what Cairo logic just executed. And in this Cairo logic, we will execute a validation of Bitcoin block on top of previous state of the chain. So as an input, you will have what is in this green rectangle at the top, which is a previous state of the chain, plus blocks that you want to verify. And inside Cairo, first, you need to verify that the proof of previous chain state is correct. We can't trust it by default. We need to verify it. And then once we have a verified chain state, we can apply block on top of this chain state, which will result in a new chain state. And once this Cairo execution is proven, we will get a proof that, as I described, can be used to do many interesting stuff. Is that more or less clear?
Yep.
More or less. Okay, let me check the chat. All right, so in order to get to this final state, we broke the project into multiple milestones, and those milestones can be mapped on such a diagram. So what we have here is what we had on a previous picture, but in a slightly more detail. So in the middle, we have this Cairo logic that verifies proof of previous state and executes consensus validation logic. And we start breaking down the problem into pieces from the middle, from this darker blue box, which is block validation. And at the beginning, we have header validation, which is the simplest thing to verify because there are not that many data that needs to be calculated, and we are somewhat near the end of that step. So the header validation is milestone 1, and we already managed to run it on a considerable amount of blocks, like 10% of total Bitcoin blocks, and we plan to run it on remaining blocks soon. Second milestone is more or less consensus rules in this transaction validation box. That's the rules that can be calculated based on the data from the block, more or less. That's milestone 2. We are somewhere near the end of its implementation. It has not yet been run on the on real data. There are some technical problems, but we are close to completion. And then there is milestone 3, which is Bitcoin script validation, and that's where integration with Shinigami or Shinigami script is necessary. That's what we are starting soon. I think that Brandon will have more details on that. That's the third milestone. And fourth milestone is UTXO verification. That's the thing that in order to spend some previous transaction output, we need to be sure that those outputs are actually spendable. And that's where this UTXO Merkle accumulator that is in the that is an input to the whole Cairo execution will help. And we'll discuss that in more detail in a minute. Michael will explain what is all this about. But that's something that will also start soon, probably in parallel with script validation. So that's milestone 4. And once we have milestone 1, 2, 3, and 4, we will have full consensus validation logic in Cairo, and we will be able to verify that it successfully runs on real blocks. And that's what milestone 5 is about. Next is a little bit unclear because we will need to run the prover on execution of all these validations. And that is not yet clear how we are going to do that. I think that we'll reach out to Herodotus. Marcello is here, or and we need to design that step and discuss it with people that have real experience with proving. Okay, that's more or less it about project scope. And if there are there any questions?
Yeah, I had a question.
Yeah.
Yeah, so in the first diagram that you showed, it's written that we'll need the Stark proof of the chain state up to block n-1. So does that mean that to verify a state transition from n-1 to n, we need the proof for all blocks up to n-1?
Yes.
Okay, so do we like recompute, or are we storing those proofs? Like, how are we storing those proofs? Or are we recalculating the proofs?
I mean, this construction is recursive. So in order to prove block n,
Okay.
you need to have a proof of block minus n. And since this previous block also is recursive, it includes information of previous proofs. So in order to run a single step of proving, of validation and proving, you need just one previous proof.
Got it. Okay, I understand. So all of them are recursive.
I mean, that's how it looks at the conceptual level. Probably in practice, in order to get proving done faster, we will parallelize. So we will be proving several blocks at the same time, or maybe groups of blocks, and then we'll aggregate those proofs recursively in another Cairo program. But these are all proving machinery details that I do not want to get into right now because that is a little bit vague.
Yeah. All right. Got it. Thank you.
Any other questions? Okay. So Michael, I'm passing this to you.
Yeah, sure. So let me share my screen. Okay. Can you see my screen? Perfect. Right. Hello, everyone. So I'm going to explain a bit more about one of the upcoming milestones. We have like two large milestones that we already started working on. It's Bitcoin script integration and UTXO. So, and I'm going to talk more about like what is like UTXO, why we need that, and what are the challenges we'll like face while working on this particular milestone. So what's the problem? So right now, what we do like in the full full block validation is we provide our Bitcoin client program with blocks like containing like all the transactions, and every transaction has like multiple inputs, multiple outputs, and every input references specific output in the past that it spends, right? Also known as unspent transaction output. And for convenience, what we do right now is we sort of expand this back reference. So if there is a like an input in a particular transaction that points to like an output in the past, right? Then we sort of like do like de-resolving and substitute this like output data to the input. That allows us to do like things like transaction fee calculation, some checks regarding the transaction finality, like and so on, right? And I mean, like it is great, right? So like everything works. So it's basically what we need for consensus validation. But the problem is this data is actually like unconstrained. What it means is when, for instance, like we do transaction encoding in order to compute transaction ID and then like compute the root of the Merkle tree of like transaction that contributes to the block header and like ultimately to the block hash. So this data, right, that we resolve like from the output, like such as like value, for instance, right? So it's not part of that. So it like this data doesn't like contribute to the final like block hash, which means that like in theory, right, we could provide basically like anything, and that would end in like double spending attacks, or we could like provide outputs that are like non-existent, and you know, like and so on. So it's like it's pretty dangerous, right? And yeah, so at this point we don't have like any like ways to you know, like restrict that. So we need like a way to do that. The most straightforward like approach, something that's like a typical Bitcoin node is doing, is we need to maintain something that is called UTXO set. So it's a subset of outputs that are like not yet spent. So like obviously it's like a dynamic set, right? So when we see like new outputs, we add them to the set. If some outputs are spent, we remove them from the set, like and so on and so on, right? So I added like an example, just like some hypothetical like blockchain consisting of like 4 blocks. At the like initial stage, we have empty UTXO set. Then we have like block 1. At the end of like this block, we have 2 new outputs. So like mark as green. And let's say like in the block 2, the first output is like spent, so it's like removed from the set, like, and so on, right? So we have like this like dynamic structure. It can be like pretty huge. Like in practice, UTXO set is like a large like set. So, and given that we are also like constrained in like how much computation we can do, we cannot like possibly store that inside like the circuit. So we need like a different solution. What can we do? So what can we do like instead is we can have like a succinct accumulator. So this is like what UTXO is about. So UTXO is like basically a commitment to this like UTXO set. And the way it's like is implemented is we like Merkleize our UTXO set. So the leaves of like the trees are hashed elements of the UTXO set, and then we construct not like a single tree, but like multiple trees. It's also called like forest of trees. And it's also like an important thing that all those trees are perfect binary Merkle trees. By perfect, it means that they have like exactly 2 power some like number of like leaves. So it's can be like 1 or like like 1 leaf, or like 2 leaves, or 4 leaves, like 8, 16, like etc. And like subsequently, if in a like a single Merkle tree, right? So we would have like a single root. So for a forest, we can have multiple roots. And so here is like an example. So you may know that some of the roots can be absent. So this is like normal, right? So in like, for instance, this particular example, I have 2 roots. So I have like root at kind of like a height 0, and I have like a non-empty root at the height like 2. And I have gaps here. I also can have gaps here if, for instance, like before I had like a larger forest, and this was like a non-empty root, but like afterwards, so forest decreased in its size, and now like those roots like are absent, right? So what it gives us. So now we have like a compact representation of the like UTXO set. And we will also call it as like UTXO state, right? And the simplified flow like looks as follows. So we have some UTXO state n, and then we wanted to process a block containing like multiple transactions, and then like for every transaction in the block, we go like over all the inputs, and we add oh sorry, it's actually like vice versa. So for inputs, we remove items from the forest, right? Because we spent unspent transaction outputs. And for every new output in the transaction, so we add new items to the state, right? And like in the result, so we will have like a new set of roots, right? We will have like a new UTXO state n+1. Okay, so this is just like a simplified flow. But like obviously, right, roots is not enough, right? Because it gives us like no information about like the actual like leaves, right? And we need what we need is a proof that specific like out point that our transaction input refers to is actually like part of this tree, right? So when you like something like beyond that, and here where we get to inclusion proofs, right? So what is inclusion proof? It's like a similar concept as like in the Merkle tree, right? So if you have like a Merkle tree and you wanted to prove that specific like leaf contributes like to the tree root, right? So you can provide like a compact proof that contains sibling nodes that you will need to like reconstruct to obtain like the root and like compare that the roots are like identical, right? It's also like called like authentication path. So here the principle is similar. It just since you have like multiple roots, right? So your proof can be like your like proof is built for a specific root. So let's take a look at the example. So for this UTXO forest, let's say I wanted to prove that this output, number one, is like it's actually, so there's like a route from this output to root at the height 2. Okay, so what do I need for that, right? So first of all, I need this output to obtain this intermediate node, and then I also need this node to compute the root. Okay, and therefore my inclusion proof for this output would consist of those two nodes, and I need like some information, right? I need information in which order I have to hash intermediate nodes, right? So for instance, like in this specific case, right, this output, which is also like called like sibling nodes because it kind of like it's near to the current node we're like working on, right? It's like on the right, which means that when I hashing like those two nodes to obtain the intermediate node, they're like parent, right? I will take my current node as a left argument, and I will take the sibling node that is part of the proof as like right argument, right? So the extra like information bit in this case is like either left or right, right? It's just like single bit of information. So similar for this step number 2, right? So my current node at this step is this one. It's like left argument, and the sibling node, which is like part of the proof, is the right argument, and the parent node is the root, right? So in this case, this extra bit of information is like again right? So if I take like the entire proof, right? So it will basically consist like of 2 nodes and like extra like net information, 2 bits, right and right. So typical approach is to store this extra information packed in a single like number, right? So since the kind of like the height of the tree is like logarithmic to the number of like leaves, right? So it's like generally like for instance, like for Bitcoin, it's usually less than like 20, like 30, like at most. And so we can like pack like everything like in a single integer. And those bits, so if you like, we'll check the binary representation of this integer, like, so we will like see those bits. So for instance, like in our case, it's like like 1 and 1, right? If you try to enumerate like all the nodes in this tree, you will actually see that those are kind of like the order, like the order of the node in the tree. And for like the specific like leaf that we wanted to prove, verify inclusion proof for. So in this case, this like integer is 3, and the kind of like the index of this leaf is also 3, and therefore, so it's usually called like leaf index. All right. Okay, so it's great, right? So now we have UTXO roots, we have inclusion proof, which means that for every like input in a specific transaction, we can actually like prove that the out point that we resolve is legit, that we do not do double spending, that we do not provide some non-existent like output, right? It's great. However, there are some edge cases, and like one of the edge case is when there is like an output that is spent within the same block it was created, right? It's possible. So like in Bitcoin, for instance, you can have 2 transactions going like one after another, and the first transaction has like a certain like output that is spent in the following transaction, right? So what's the problem here? The problem is the UTXO state is like changing like within the block, right? Because recalling that for every input, we like removing items from the forest, meaning that we update the roots, and like for every output, we add new items to the forest. So we update the roots again. So basically for every input, like an output, UTXO roots change, right? And this is some like intermediate like UTXO state. So we kind of like know it like in advance when we like provide it, right? I mean, we could do that, but it would like require us to kind of like redo all the computations, right? And if we do not like know this like intermediate state in advance, we cannot generate like an inclusion proof, right? Because we kind of like possibly know like what are going to be like the roots at this specific like state in between like block processing. So what to do like in this case? In this case, we sort of like falling back to like a simple solution. Like the simple solution is we just like maintaining like the UTXO subset, which is like in this like edge case will be like relatively like small, right? So in most cases it will like empty, but there are like some blocks where it will be like non-empty. Moreover, if let's say we wanted to process like multiple blocks like at once, let's say we want to process like 6 blocks at once, right? We can have this UTXO set relevant for this particular like block batch, right? And yeah, and like this is like how we can kind of like cover like this specific edge case. In the code base, you can spot the notion of cache. So this is like what cache is about, right? So cache outputs is basically this specific UTXO subset, which contains like outputs that are going to be spent within the same block or within this span of blocks that we're like currently processing with our clients. And you will also see that transaction like outputs and transaction like inputs have this cached flag, which is sort of like hint that says, so this output is going to be spent like within the same block. So put it to the cache. And subsequently, like for the inputs that reference cached outputs, we need to check that this output is like actually stored like in the cache. Right. So finally, right. So what is the data flow when we enable UTXO? So in the like kind of like the baseline is we get Bitcoin blocks from somewhere, right? We get blocks with all the transactions, like either from the like Bitcoin public RPC node or from some indexed like service that provides us with the can provide this information, let's say like in a single request. Doesn't like really matter. So then we have something that is called UTXO backend. So it's sort of like in the middleware that extends the data that we obtain from the Bitcoin data lake, and what it provides on top of block is, first of all, like a subset of like UTXOs that are going to be spent by the inputs in those blocks, and inclusion proofs for all those UTXOs except for the cached ones. Okay, and so I mark like this data in like one color, so it's not part of the state. So the state, right, is like something that is our like Cairo client maintains like throughout like the entire Bitcoin chain. And so before it was just like the chain state, right? So basically the like information about like the current height, like the best block hash, like etc. etc. So now it is like extended with the UTXO roots, right? So the roots of our Merkle forest, and at the end of the execution, right? So we have new chain state, and now we have also new set of UTXO roots, right? So that we kind of like return as the result of our program and update in our UTXO backend. All right, so that's pretty much it. So that's what I wanted to kind of explain in more details. So we already have started working on several tasks related to that. So we now working on basic primitives. So basic primitives are how we add new nodes to this Merkle forest, how we remove nodes from the Merkle forest, and how we build inclusion proofs, how we verify inclusion proofs, because this is like what is necessary to be done on the Cairo side. Once we have those primitives built in Cairo, like a second like important task would be creating this backend that's going to maintain the UTXO set, that is going to generate inclusion proofs and provide this extended program input that will allow us to run consensus validation now with constrained outputs. Okay. Yeah, thank you for listening. So if you have like any questions, please feel free to ask. Also, yeah, let's follow up like in the chat if you'd like, because it's a complicated subject. Yeah, I think so. We will like spend like a lot of time try like to dig in.
Maybe just one question. The proofs that are in the arrow below, at the bottom, sorry,
Yep.
are Merkle proofs, right?
You mean this one, right?
I meant in the at the bottom of your schema.
Mhm.
Yeah, you have proofs going from the UTXO backend and to the Cairo program. These are Merkle proofs, right? Inclusion
Yes.
proofs.
Yes.
Okay. So my question is, very naively, I expect a Cairo program to be used to generate Stark proofs, but I don't see any Stark proof here. So why do we need a Cairo program here? Why don't we just
Yeah.
plug it in?
So right now, so kind of like the Stark proof is like outside of this code. So
Okay.
like more broadly, right? So like ultimately, I mean, if you kind of think of this as like Bitcoin client, right? If you run like a Bitcoin node, right? So you don't kind of like, like run it for like one block and then you like run for a second, like a third. You just like run like a daemon and it like does the job, right? So like ultimately we would want to do like the same, but for like a Cairo program, just like run it once and like infinitely, okay? But we cannot do that, right? Because there's like no way to like efficiently prove large or like infinite like computation like in Cairo, right? So it's something that, for instance, like RISC-0 approaches with continuations, right? Or there's like a bunch of like techniques for incremental verification. So in Cairo, there are like no like efficient techniques like yet, right? And therefore, so after we have like everything like implemented, like full like consensus validation, we will like approach proving, which will likely require some sort of like continuations like as well, just like built on the application level, right? And it will be like more or less like agnostic to specific like computation, meaning that it doesn't like really matter whether like the inputs of your program, whether like the outputs of your program, like all matters is that you just have some like links, like backlinks that connect like together multiple invocations of the program so that you can recursively prove it like afterwards. So I actually have like so this is like one of the proposal, like proposed approaches, like how you can do that. So like in a nutshell, right? So this is
Michael, sorry to interrupt you, but maybe let's not dive into this rabbit hole. I mean, we will have more community calls to discuss this.
sure. Yeah.
Maybe
yeah,
let's give Brandon some time to explain the Shinigami integration, and maybe we will come back to Marcello question at the end.
Sure. Yes.
We can organize another community call next week to discuss recursion continuations, and maybe we'll even have more to say than we have today.
Sure. All right. Thank you, everyone. Yeah, Brandon, please.
Yeah, thanks. I feel kind of bad. I didn't prepare cool diagrams like y'all did. So I will maybe just share some things that I found online that I think are useful to see while I'm talking. So I'm not just talking into the thin air. Okay. So essentially, let me get to the tab I wanted to show. Okay. Essentially, we kind of talked a bit about, or a decent bit about, inputs and outputs of transactions from Maciek and Michael. But there's like this kind of point between spending the inputs and the outputs that we kind of glossed over, and that is verifying who owns the inputs and verifying kind of who and how they're able to spend these inputs to get these outputs. So you can kind of imagine there's like this extra spot in the middle on transaction C where Shinigami script execution comes in. So how Bitcoin script kind of works at a high level for people that aren't familiar, is it's like a stack-based programming language in a way. It's like very low-level assembly where you can push and pull things from a stack. But the most common type of program that's done on Bitcoin is just verifying a signature. So if you own the private key for your Bitcoin wallet, you're able to spend the inputs from your transaction. And what that script kind of looks like is something like this in this picture. Essentially the input, so every single input in a Bitcoin transaction will have I think this is a good picture. Every single output in a Bitcoin transaction will have its script pub key, which will be linked to the input when you go to spend it. And that script pub key is essentially a program that the person that spent the Bitcoin last time set onto the output, saying that you can only spend this Bitcoin in a certain way. And we call that also, instead of a script pub key, you can call it a locking script. So this locking script comes from the output of an old spend on a Bitcoin transaction. So in an old UTXO, it will have this locking script that will essentially usually will hold the spender's public key. So if the spender wants to be able to spend the Bitcoin inside this output, and send it to their friend or send it to a separate wallet that they have, they will sign the transaction, and then they will link that into the transaction data itself. So we call this usually a script signature. You could also call it like a spender script, and it will be its own separate Bitcoin script, and it could be any arbitrary logic with some bounds. But in this usual example, that spender script will just be the signed transaction data. So the spender script will run first, and it'll push the signed transaction data to the stack. And the locking script will push the spender's public key and then check that, in fact, the correct private key signed that transaction, which will result in being able to spend the outputs here in transaction C. So they'll provide their signature for the input at the top and the input at the bottom. Shinigami script will run and execute all of the Bitcoin like ins and outs and the logic that they have in script, and then say, hey, this is actually a valid signature. So the user can spend these outputs. So how it will integrate into Raito, or the consensus side, is that when we're validating transactions, so every single transaction that we run in a block will need to be validated to be correct, in order to be fully confident and have no trust assumptions on the existing miners or any kind of potential like people trying to send fake transactions to the Stark proof network. It will validate the script execution, proving that these inputs on the left were in fact spent properly by the right people, resulting in a valid state transition. I won't go into too many details on how script works because I've done it in previous calls, and we'll, like Magic said, we'll have a lot of time in the future to go deeper and deeper. But yeah, I'd recommend reading this, like Learn Me Bitcoin, if anybody's interested, not only in the script execution, but it goes into detail on like everything that I think we covered today. Maybe not UTXOs, but yeah, I think that this GIF also kind of explains it, where they push the signature onto the stack and then the script sig, and then check that or the script pub key, and then check the signatures. But yeah, I mean, that's pretty much it. I won't go into too much.
I think that what makes sense to discuss is some technical details about integration between two projects, because right now we have two projects. They were developed separately without spending a lot of time on how to integrate them. For example, right now both projects have a transaction model, and these are different Cairo structures, and since those transactions can be large, we probably do not want to to create adapters in Cairo, which will rewrite data from one structure to another. That is a problem that we will need to solve. Another problem is that in order for Shinigami to be ready for consumption as a dependency in Raito, we will need to add some structure to it, like create a crate that contains just what is necessary for script execution, because right now Shinigami contains a lot of logic that is absolutely necessary for testing, but should probably not be imported as a dependency in Raito. So we have some refactorizations before us. How to do it exactly, it's not yet clear. We will need some technical discussions.
Yeah, thank you for clarifying that. Yeah, I think the main thing that you had mentioned that Raito will be using is the engine. For people that are familiar with the Shinigami code base, there's this engine that kind of executes transactions, assuming that all of the data provided about old transactions like UTXOs and about the transaction itself is correct, which will be validated by the consensus rules on the Raito side, and then just kind of be passed in into the Shinigami side after it's kind of integrated through the crates and things like that. So we'll have to, I think we had already kind of talked about this before, but two big things that I think we'll be doing on the Shinigami side to help with the integration is one, splitting it into crates like Maciek just mentioned, and also making this transaction type more generic, so that any library or like any program like like Raito that's using it can define their own transaction structures that are more efficient for their use cases, as long as they're able to provide the info that we need inside the engine. Like, I think the main two things that we'll need is the hash of the transaction, which is used to validate signatures, or like it's used to validate signatures in a way, because the person will sign the hash of the transaction. And we'll also need things like the lock time for certain opcodes. But yeah, that's kind of the high level idea.
Thank you. So since we have a couple more minutes, maybe let's have a look at the question Marcello posted in the chat before he had to leave. So he asked, in general, he asked about reorgs and what will happen if the base chain that we are building a client for will reorg. And I think that right now it is a little bit out of scope, because what we are building is about proving a single step. But whatever is built on top of this will for sure need to follow any reorg behavior of the base chain. I mean, that's my general answer to this question. How it will be designed in detail is not clear to me. It probably depends on the application, because the answer will be different whether it is, for example, a ZK client for initialization of the Bitcoin node, versus whether it is a ZK bridge to another blockchain which has its own reorg behavior, and the question is how to combine two of them. So that's the kind of design questions that needs to be answered before giving any specific answers. Okay, any other questions? All right. So if not, I think that's it. That's the end of the first joint Raito Shinigami community call. Thank you for attendance, and see you in the next ones. Bye bye.
Thank you.
Thanks so
Thank
much.
you.
Thank you.